This video will quickly walk through what we worked on in the week 24 class. So follow along with the notes and pause the video if you want to do a little more writing than I'm leaving time for, because I'll just go through the slides pretty quickly. So first of all, we looked at this advertisement that I found in a magazine a while back. It says over here, topic: hair building fibers are organic electrostatically magnetized hair fibers. So this is an example of how in our popular language, the way we commonly talk, electrostatics and magnetism often get mixed together. But when we look at how things really work, those are really two distinct phenomena. So basically using the electric attraction between objects to attach little fibers to hair to make it look like a fuller head of hair. This part here follows up actually on last week's notes, so you'll need last week's notes packet if you want to see where this is, but I just wanted to do a few things that were applications of what we worked on last week. So last week we talked about an electromagnet with a core, so as in a nail wrapped with wire. And today in class we got out our battery pack and wires, and then I passed out a nail that was wrapped with a solenoid, and students used that to pick up paper clips. So basically took a moment to play with electromagnets today. In the homework, you studied last week the applications of an electromagnet, so if you have any questions about that, let me know. We looked at the buzzer and the circuit breaker. And then part F, this is at the bottom of the last page of last week's notes. We talked about the fact that magnetic fields exert a force. And we talked about that they exert a force on magnets, and you can see that if you bring one magnet near another magnet, or if you have a magnet near a magnetic field. So I'm sorry, a compass. A compass is a magnet, and when you put it in a magnetic field, that will make the compass needle turn. That's because the magnetic field is exerting a force on that magnet, that little compass needle. And secondly, magnetic fields exert a force on particles with electric charge. Particles with electric charge, such as a proton or an electron, they have to be moving. If they're not moving, they won't experience a force from the magnetic field. We talked last week about charges moving in a wire, so that's a current. And we did a little experiment last week with little tinfoil wire with a magnet under it. And we discovered that the force, direction of the force can be described by the right-hand rule, where here's a little diagram here, the flat hand, where the thumb is the current or the movement of positive charge, meaning the velocity or the direction that the charge is moving. The fingers represent the magnetic field, B, and then the palm represents the magnetic force. Today in class, we did two little applications of this, the simple motor and the loudspeaker. This is what the motor looked like. It was a coil of wire with two longer wires going off the end. We supported those on a bent paper clip, and then this makes our complete circuit. So the charge can flow through the wire, up to the paper clip, over here, through the coil, over here, then makes another contact with this paper clip, then back through the wire to the battery. This wire has a different kind of coating on it than these other wires. These have sort of a rubber plastic coating, the connecting wires. This coil has it's copper wire with an enamel coating on it. So the enamel is like a paint, and it is an insulator. So that's why we can make a coil like this and not have the charges, going across from one part of the coil to the other. And then under the coil is a magnet. Turn to this page in your notes, a simple electric motor. What we want to do here is analyze at point A and point B, what is the direction of the current in the wire, what is the direction of the magnetic field, and what is the direction of the force at each of those points. So you can take a moment to do that. So the current at A is to the right, the magnetic field is up in both places because this is a north pole, so the magnetic field is going upward out from that north pole. And the way we got the direction of the current here was this is the positive terminal, so if you follow the flow of positive charge, at this point it's going to the right, and then as you get down to point B, it's going to the left. Repeat the same process over here. And now we're ready to apply the right hand rule. So if you put your right hand here with your thumb in the direction of the current, your fingers in the direction of B, you'll find that your palm is facing out towards you, out of the screen. So we would represent the force at A with a dot. Continuing to do that for the other locations on both diagrams, you'll find that for the first picture, at A the force is out of the page. At B it's into the page. What will happen? Well, that's going to make the top of the coil move forward and the bottom of the coil move backwards. When you repeat the process here, you find that now the bottom of the coil is moving forwards and the top of the coil is moving backwards. So what's going to happen is that coil is just going to flip-flop back and forth, not actually going to spin, which is not going to work very well as a motor. So here's how we solve that problem. The basic approach is to turn off the electricity in one half of the cycle. So basically give it a force to try to make it start rotating, then turn it off so that there won't be any forces when it's in this other orientation, and the inertia will just carry it through that, and then when it gets back over here again, it'll get another push from the force. So how do we turn off the electricity? To get continuous rotation, we turn off the current every half cycle. This is accomplished by leaving the insulation on one half of a coil lead. So on the left-hand side here, regardless of which side of the coil is up, I have stripped off all of the enamel all the way around. So that would be like showing the copper here with no green insulation left. This is an end view of the wire, greatly magnified. On the other side, you can see that when the coil's in one orientation, there's insulation here on the top, but then when I flip it half a turn, the insulation has been stripped off. And that's what we're seeing here in this diagram. That way, when the coil is oriented with the insulation down, there is not a continuous conducting path because that insulation is between the copper and the paper clip. So current does not flow and there are no magnetic forces. And then we set up the motors in class and watched them spin. The next application of this is a simple speaker. And here we have a soda cup with a coil of wire here taped to the bottom, and then the two ends of that wire are free, and the ends are stripped off and connected with alligator clips to a cable that plugs into like a phone or a Walkman or a CD player or whatever you play music from. And I'll let you go ahead, pause the video, and read the description here of what happens. But we were able to hear the music coming out of the cup. So continuing with part F now, that was all about charges moving in a wire. We looked at some applications of that. Now we'll talk about free charged particles. A free charged particle just means it's not in a wire. It is loose, able to move in any direction. So following along on the new page of notes now, we have the question, when will a charged particle experience a magnetic force? And here is an example. You can read the description there of when it will experience a magnetic force, and then let's apply it to this example. So this object is not moving, so there will be no magnetic force on it. The second charged particle is moving, so that's the first criteria, and the second one is that some component of the velocity has to be perpendicular to the magnetic field. Here all the velocity is perpendicular to the magnetic field, so there will be a force on this one. This one has a velocity parallel to the magnetic field, so no force on that one. There is a force on this fourth one, and there is no force on this last one. What is the direction of the magnetic field? The direction of the magnetic field is perpendicular to the velocity and perpendicular to the magnetic field. You can predict the direction using the flat right-hand rule. And then what we did was we applied that to this example, and we found that, for example, for this one, if you line up your thumb with the velocity and your fingers with the magnetic field, you find that the force is out of the page. Here's another example. Pause the video, figure out the direction of the magnetic force on each particle. And I should mention this blue particle is supposed to be in the magnetic field, not down here. And the blue one is negative. For finding the magnetic force on a negatively charged particle, you can either use your right hand and then take the opposite of what you get, or you can use your left hand, since your left hand is the opposite of your right hand. Once you have the force, hopefully it looks like the green arrow here. And the question is, will this force change the object's speed? And the answer is no, it will not. And that is because the force is completely perpendicular to the velocity. In order to change the speed, you would have to have at least some component of that force that's parallel to the velocity. So this will not change the speed, but it will change the direction. And let's take a look at what happens when it changes the direction. So when it changes the direction, that tells me because the force is upward, at some later point in time, rather than being here, the particle would be off to the right here if there was no force. Because there's a force, it's going to be a little bit farther up than that. So I know the particle is going to be to the right and a little bit up at some later time. Now let's figure out at that new location what's the direction of the force. Well, the new direction of the force is still going to be perpendicular to the velocity. But the direction of the velocity has changed, so use your right-hand rule and you'll find that the direction of the force is now in this direction. And if you see what's going to happen, this process is going to continue, and we're going to end up with circular motion because the force is always perpendicular to the velocity. The velocity is not changing, and we're going to end up with a circle. And same thing is going to happen here. This one is going to be going the opposite direction, however. How do I calculate the magnitude of this magnetic force? The equation, using the hints down below, you can read these, but the force is going to be directly proportional to Q and to V and to the magnetic field. So the equation is magnetic force equals Q times V times B. And let's take a look at the units. To find the units, we can first solve this equation for B and then substitute in the units. So we would have B equals force divided by Q times V. So force is newtons, Q is coulombs, and V is meters per second. And that whole combination of units is called a Tesla. The other way you could look at this as coulombs per second, which is an amp. So also a newton over an amp meter, but not an ammeter, is a Tesla. A 1 Tesla magnetic field would cause a force of 1 newton on a 1 coulomb charge that is moving at 1 meter per second perpendicular to the field. What are some realistic magnetic field values? Well, conventional laboratory magnets would be up to about 1.5 Teslas, superconducting magnets about 30 Teslas, and the Earth's magnetic field at the surface, you can see how weak it is, 5 times 10 to the negative 5 Teslas, so much smaller than the laboratory magnets that we're using. Here is an example. Go ahead and pause the video and solve this. Here is the solution. So calculating the magnetic force using Q times V times B, and then we can use circular motion methods to find the radius. You also need to be able to draw a diagram and predict the direction of the pathway. Then we took a little bit of an aside here and talked a little bit about what things are made of and how scientists have discovered that. So everything's made of atoms. We have a picture here of the atom. The nucleus contains the protons and neutrons, and then inside the protons and neutrons are 3 smaller particles called quarks, and then the gluons are holding those together. How do we know? Well, a lot of this research has been done at many different particle accelerators over many years, but currently this research is being done at the Large Hadron Collider at CERN, which overlaps France and Switzerland. It's a huge ring with a tunnel, which is underground. You can see the scale here. So, the whole thing is maybe 5 miles in diameter. The tunnel is about 574 feet below ground. And I'll just pause it and you can read the descriptions here of what's happening. But this is showing the tunnel underground, and it's showing here that there are buildings above ground that connect to the detectors that are underground. The detector is about 15 meters in diameter. You can see the scale here is a little person. And go ahead and pause it if you want to read what's happening. But the pipe, the beam, the tunnel, the beam that's carrying the particles that are going around would be perpendicular to this area here. So the particles are going to collide right in the middle and then spray out other particles, and then all these different layers are designed to pick up and track different information about those particles that come out. Identifying the charge of particles. So there's a magnetic field in the detector. This results in a magnetic force on moving particles that have an electric charge and causes these particles to move in a circular arc. Positively charged particles will curve one direction and negatively charged particles curve the other direction. The direction of the curved path enables researchers to determine the sign of the charge on an unknown particle. Notice that the neutral photon traveled in a straight path. It did not experience a magnetic force. This is one of the applications of the fact that there is a magnetic force on a charged particle that's moving in a magnetic field. Now we want to move to a new topic. This is standard M3. And the big question here is, if moving charge causes a magnetic field, and we're convinced it does because we've seen these two examples of that, is the reverse also true? Can we use a magnetic field to cause charge to move? So here we started with moving charge, and that produced a magnetic field. Can we use a magnetic field to produce moving charge? Basically, can we make current flow by using a magnetic field? And what we have here, what we did in class, we have a very sensitive ammeter, and it's an analog one, not digital, so it has a little dial here with a needle that moves back and forth. There are two knobs here. We connected a wire to the two knobs, and then we connected a coil to it to make a loop. But there's no battery. This is just an ammeter, just to measure flow of current. And then you'll see the coil in a moment. But what this important, the reason for the zooming in here, is that if the needle deflects to the right, that means, let's see if I can stop it. If the needle deflects to the right, let's go back. If the needle deflects to the right, see this little arrow here, the two dots in the arrow? That's telling you that inside the ammeter, the current flowed from this terminal to this one. So the right pointing arrow means that if the needle deflects right, the flow of charge inside the ammeter was this direction, which then tells you that outside it was that direction. Okay, so let's continue on. Okay, so let's remember that. Here's the coil of wire connected. So we have one big loop with the ammeter in it. This is the smaller loop. Now this is the north pole of the magnet. The north pole of the magnet is going to go towards the coil. And when this happens, my coil actually kind of falls off of the supports I have it. But the main idea is that the north pole is going towards the coil. I want you to watch the dial or the galvanometer, which is an ammeter, and see which way the needle goes. Okay, so did you see that? The needle went to the right. So that's telling us, what that means is that when that north pole went towards that coil, current started to flow in this circuit that we made. And the direction of the current was from this terminal to that one, and then out in this wire, then through the loop, and then back to this wire. So in your notes, here's how we drew these pictures. We took data using this. What we have here is in number 1, north pole moves down toward the coil from above. And that is, that's the situation that we just watched on the video. Here's the north pole, here's the coil. At time 1, the north pole is far away from the coil. At time 2, the north pole is close to the coil. So what happened between time 1 and time 2? The action that was taken was that magnet was moved towards the coil. And then a current was induced. And this is my sort of cartoon drawing of our experimental setup. You can see this is the galvanometer. This little part of the wire just shows the movement of charge inside the galvanometer. And then out here, this would be a connecting wire. This is the red coil, which really has more than one loop to it. And then this is the other connecting wire going back. Okay? The first thing we want to do is draw the magnetic field inside the loop. The important thing to remember for these diagrams is the observer is looking from above. So the observer is up here looking down into the coil. When we draw that, you need to think about the magnetic field of a bar magnet. Here's the magnetic field lines, and this is drawn for a magnet where the south pole's near the loop, but you get the big idea, then you can apply it. So if you look at a loop that is far away from a magnet, you'll see that in this drawing you can see about 3 magnetic field lines actually go through that loop. Then if you move the loop much, much closer, look how many magnetic field lines are going through the loop now. So we have this idea of magnetic flux, which is the intensity of the magnetic field passing through the area of the loop. So here we have a low intensity, just 3 magnetic field lines. Here we have a much higher intensity of the magnetic field. So this one has more magnetic flux, more magnetic field lines passing through there. So how do we draw that? Here is how we draw that. So the North Pole, remember the magnetic field lines are coming out of the North Pole. So if you're looking at that coil from above, you would see magnetic field lines going into the coil, like into the page. If we look at the coil, here's the picture from above. So I drew 4 X's to represent magnetic field going into the page. Now here, at time 2, the magnet is much closer. So, right, we're going to have more lines now passing through that loop. So instead of 4, I'm going to draw 6. Just doesn't matter how many you draw, but I'm going to draw 6. So you can see that we've had an increase in magnetic field lines penetrating that loop. Then we need to actually take our data, which explain how I knew which way the current was flowing here. So in the video we saw that the needle deflected to the right, which tells us that inside the flow is this direction. So if the flow is this direction inside, remember it said that the flow was to the right between terminals, then the flow out here must have been this way. And that's how I can get the flow inside that coil. And the last step, this bottom picture is just a redrawing of this loop here. We want to draw what magnetic field then is produced by that current. So this magnetic field, using your right-hand rule, the first right-hand rule where you curl your fingers, you can see that the magnetic field will be coming up inside that loop. Okay? Then we repeated the process with the second situation where the North Pole moves up away from the coil, and these were our findings. So make sure that you understand where these diagrams came from. This was a result of our observation in class, our data. And then once we knew the current, we could figure out, using our right-hand rule, that the magnetic field induced by that induced current was into the page. Now, can we find a pattern? How does a change in magnetic flux relate to the direction of the induced current? And this page just shows here a summary of the analysis that has already been done on the 2 examples we did, 2 observations. Can you see a pattern? Can you see a pattern? How does the change in magnetic flux relate to the direction of the induced current? You can pause it and think about it to see if you can find it yourself before I tell you. Okay, here's the pattern. Here we had 4 X's, here we have 6 X's. So we had an increase in magnetic field lines into the page. What was produced was a magnetic field out of the page. Here we had a decrease in magnetic field lines into the page, and then what was produced was more magnetic field lines into the page. So the pattern is that whatever the change was, here we had more X's. The induced magnetic field by that induced current is going to try to cancel out the changes. It's going to try to keep things constant. So it's trying to keep things at 4 X's. Here we have 6 X's, but if it produces 2 dots, then in combination, since 2 X's cancel out 2 dots, we're left with 4 X's. Here we have 6 X's, but that decreased to 4. So to try to keep it constant at 6, it makes 2 more. Then what we did was we used that pattern to make predictions. So we predicted that since this would have a few dots going to more dots, that the induced magnetic field should be X's. If the induced magnetic field was X's, what kind of current would produce that? Well, that would have to be a clockwise current using the right-hand rule. And then a clockwise current would create a leftward movement of charge through the galvanometer, which for this galvanometer would be a leftward motion of the needle. And then we actually did the experiment and found out, yep, that's what happened. So it supported our pattern that we found. And same thing with the south pole moving up away from the coil. But check this, make sure that you can follow the logic of how this all worked. So then Lenz's law is the official name for this pattern. When the magnetic flux through loop changes, a potential difference is induced in the coil. Also, many times that's called an EMF, electromotive force. If there is a complete circuit, this potential difference will cause an induced current whose magnetic field opposes the change in flux. And then we did 3 examples. What is the direction of the induced current in these examples A, B, and C? So some practice. A round loop is pulled to the right out of a magnetic field which points out of the page. Whenever you do these, I would highly recommend that you draw a time 1 picture, a time 2 picture, and then your final picture which shows the induced magnetic field. So I don't have those here, but if I was doing this, I would draw 2 circles. For the first circle, time 1, I would draw 4 dots. For the second circle, time 2, I would draw no dots because the loop would not be in the magnetic field anymore. And then I could see by looking from time 1 to time 2 that I have decreasing dots. I went from 4 dots in there to no dots, which means really 4 upward magnetic field lines to no upward magnetic field lines. So then the induced current is going to create a magnetic field that is upward to try to compensate for that loss of upward magnetic field lines. Well, what kind of current is going to make an upward magnetic field inside there? It's going to be a counterclockwise current in the loop. Okay, so try this one, and then pause the video and try it, and then check your answer. So here's the answer. And pause the video. This picture is a little bit maybe hard to interpret. There's a loop, and then underneath it is a bar magnet that's moving upward toward the loop. And here's the result. In our very last topic, we looked at magnetic flux, and I don't have the whole definition here on the slide. So pause the video, read the box on magnetic flux, and this should say number 1. Number 1, rank the coils from least to greatest magnetic flux. The first thing I want to emphasize from the reading in the box is that we don't usually think of area as a vector, but in physics we do assign it a direction. The direction of an area is perpendicular to the surface. So if you were to think of this coil, which here we're looking at the side view of a loop of wire, a coil, the area vector would be perpendicular to that flat surface. If you imagined like the head of a drum, it would be perpendicular to that imaginary surface. So the green arrow here is the area vector. You'll see here that it's always perpendicular to that surface area. So basically magnetic flux, a good proxy for it is the number of magnetic field lines that pass through the area, that kind of you think about like puncturing that drum head. So coil 3 has the most magnetic flux. Look how many magnetic field lines pass through that area. Here, we still have magnetic field lines passing through, right? But not as many as in that one. And this coil 1 has none. So the order would be 1, 2, 3. Then we want to calculate the flux. In order to calculate it, you need the area of the loop, the magnetic field, and you need the angle between the area vector and the magnetic field. And these are circular loops, so we have the area of a circle. So first I found the area for all of them, and then calculated the flux. So take a look at those calculations and make sure that you can do those on your own. And that concludes the week 24 super fast overview of the class.